So unlike what we had on the first order linear differential equations, we are going to see that the second order linear differential equations, there is a lot for us to consider there. So it is a continuation from the first part that we had. Make sure that you join the membership so that you'll be able to access or to watch the first part that we had on the first order linear differential equations. So this is, or all this part that we are doing is actually as a request of the members. That is why we are having these videos that we are actually seeing now on N6. So we just hope for more to come before our exams. So like I was saying, there's a lot that we need to work on from the format first. So you're going to see that a second order differential equation is the one that is going to be written in this format, whereby we are now having a second order of the derivative in that case. All right. So we are having the second order of the derivative, which is this one as the highest part that we have. And to be a linear, that means that it is being raised to the exponent of a 1. It must not be raised to any exponent. That whole part, we are not supposed to have that, okay? Being raised to any exponent is just supposed to be a 1 there. So these are the typical questions actually in your syllabus. So that one, there's no need for us to even worry about. So you're going to see that the A, the B, the C are constants. So in this case, you're going to have A, B, C are constants, which is these are numbers that we have that you're given. All right, so what is it that you're going to consider, or what are the steps that we are going to have in solving? So in order for us to solve, the first thing that we are going to have whenever you see this type of an equation, you are going to form what is called the auxiliary equation. So you form the auxiliary equation. All right. What is this equation that we are referring to? How? So the auxiliary equation is the equation that we are going to have if we let the part of dy dx, the part that we have dy dx, this one, if we let this part to be equal to r. So we're going to do this by letting, all right, so the first thing, I'm going to let dy dx to be equal to r. So some other textbooks, they use m. So I'm going to use r there because that is the one that you have from the formula sheet. At the end of the day, that is the one that you're going to have in exam. So you just have to get used to that one. So you let this to be equal to r. We let y to be equal to 1. And also you are going to let the f of x to be equal to 0. So you let this to be equal to r, this to be equal to 1, that is y to be equal to 1, and f of x to be equal to 0. So if you do this, if you substitute in place of dy dx, and we substitute it as r there, we'll see that this here is same as we've got dy dx squared. So in place of this, you're going to put what? R there, because it's being raised to the power of 2. So that means here we're going to have a r squared plus b. In place of dy dx, you're going to put what? You're going to put r there. Where there is a y, we're going to put a 1. So that's 1 times c, which is c. And remember, I said our f of x must be what? A 0. So you're going to form an equation of this nature. This is the type of equation that you are going to form. That's the auxiliary equation. So you are supposed to solve this equation. All right, you're supposed to solve this. Okay, so let's consider solve auxiliary equation. All right, solve the auxiliary equation. That means by solving this, you're going to find the values of what? The values of R. It's a quadratic equation, as you can see. The equation that we have here is a quadratic. So it's either you are going to formulate the quadratic formula. I do not know. You're going to use the quadratic formula. You're going to use the factor depending with what you have. Is it possible for you to factorize? Or there are no factors. I'm supposed to use only the quadratic formula. But after solving for this, after solving this auxiliary equation, you are going to have two solutions because it's a quadratic. But as we know that from our quadratic equation, we can have equal roots. We can have roots that are not equal, or we cannot have roots at all, where these roots are referred to as complex solutions. Remember from your N4, when you're dealing with complex numbers, you were solving a quadratic equation of this nature, -1 plus or minus the square root of -4 over 2 like this. Then you end up introducing a j or introducing I like that. That is, the roots were complex. We couldn't manage to have the solutions there. We ended up introducing j. So these are the typical roots that we're going to have at the end. So what I'm simply saying is that if after solving this, you see that your R1 is not equal to R2, from these solutions, you form what is called the complementary functions. So let me just write it here. So from these solutions, form the complementary function. All right. What is called the complementary function? That is the question. So the complementary function is the one that we're going to have from the roots. It is determined from the roots. We also have this part from your formula sheet. If R1 is not equal to R2, it means the solutions are not the same. In that case, therefore, we are going to see that the complementary function, which is the major part of our solution, which is given or can be written as YC, for the complementary function. So we are going to see that if these solutions are not the same, the complementary function is going to be given as YC is equal to AE to the exponent of R1x, which is the first solution, plus B e to the exponent of R2x, which is the second solution. So R1 and R2, these are the solutions that you're given here, R1 and R2. So A and B are constants to be found. All right, these are constants to be found. So meaning to say, you have to find this. So that is where we're going to be talking about the particular solution where now you're finding A and B. But if you just use the A and B, it means you have got what? The general solution before the particular solution. So we shall talk about that as we solve it. What if we have a condition that these solutions, they are actually the same? So we can have that. If R1 is equal to R2, the solutions are the same. Therefore, your complementary function is going to be presented by this equation, e to the exponent of Rx. Remember, is the same. The R that we have here in the cell is the same. So that is the same R there. So it is going to be A plus Bx. Where again, A and B are constants to be found. So this is what we have in each and every condition. So it is the same thing again if you've got a condition where your R is giving us, or the solutions that we have there are complex solutions. So complex solutions, we're going to see them in the form of A plus or minus JB like this, or we can use the letter I to represent what? The complex solutions. Whenever your solutions are complex, whether you write this in terms of J or you write this in terms of P, in terms of I like this, the complementary function, which is YC, is going to be given by this. It is going to be e to the exponent of AX, which is this A. So it's e to the exponent of AX into, that is A cos of BX now, which is the B, this one. So it's going to be cos BX plus B, the sine of BX. So like I said, this part here, we are not supposed to worry about this one. This is the part that we have from our formula sheet. We are given this part. So all you need is to solve your equations, then figure out, are they not the same? Are they the same? Are they complex solutions? This will be the complementary function, one of these, depending with the solution. So the complementary is determined or is controlled by the solutions of, or the solutions from where? From the auxiliary equation, this one. It is the one determining or controlling our complementary function. Okay. So we are going to see that in actual sense, we are supposed to have a combination of these two things. Sorry, that's the third stage now. We are now at the complementary function. We now determined our complementary function. The other thing to be determined is the particular integral. So you also need to determine the particular integral. Okay. So the question is how? And what is it that we are referring as the particular integral? That is your YP. Okay. We saw that the complementary function was determined, or it was controlled by the solutions of the auxiliary equation. This time, the particular integral is controlled by the f of x, this one. From the original equation, your f of x, this one. It is the one that determines or that controls this particular integral, the f of x from the original equation. So this one is determined or is found from. So it is determined from the f of x, from the f of x of the original function. All right, the original function that we had before, that original function, f of x. So you see that your f of x there can be a linear, your f of x can be a quadratic, it can be an exponential, whatever function that you're given, that is the one that controls. So assuming that everything that we are having there is not as what we are given from the f of x, which is from that original equation that we had before. We are going to see this. Let us just separate. We are going to see this. The first thing, if let's say your f of x, because you'll be given that format. All right, let me just rewrite so that we see the f of x that I'm referring to. Remember, from our original equation, we had a y dx squared plus b dy dx plus cy is equal to f of x. So this is the one that we are mentioning or that we are talking about. So let's consider that we have seen this. that f of x is equal to k, which is a linear, which is a constant, actually. It's not a linear, this one, say it's a constant. Consider, for an example, a constant. We can just take maybe aj, f of x, maybe there was a 3, or there was an 8, or there was a 7, whatever number that you have here. What is going to be your particular integral? So it is just like what we had on the complementary function. If the solutions are this, how are you going to write your complementary? It's something. So if it is a constant, how are we going to write our yp, which is the particular integral? So therefore here we are going to have yp, the particular integral, given as c, just a constant. Why using c? The c that we are seeing here is this one. Is taken from here. We used a and b already. We exhausted these one, the letter a and b, from these two. From this particular, from this complementary function. There was a and b. We worked with a and b there. So already the constants to be found, a and b, they are used. So we have to continue from a and b. Already we have used a and b, so meaning to say we are going to start at what? At c. If we have used a, b, and c, meaning to say yp is going to be the next constant, which is a d. That is what I'm simply trying to say. All right. So this was our first condition when this is a constant. You have this as a constant. You can have your f of x, this one, as a linear expression. As a linear, meaning to say we are talking about the condition of the mx plus c. Remember the linear equation. Maybe for an example, the part of f of x there is given as 3x plus 7. It's a linear part. This one. So therefore, on this manner, you're going to see that your particular integral is going to be given as, like I said, we start from c, but we have the same format of a linear, but just that we maintain the constant c, d, and so on. So it is going to be cx plus a d. We just take the same format of what? Of a linear, mx plus c, but it's just going to be cx plus d. These are the constants to be found. Same format. The constant c, k here, so it's just going to be yp is equal to c. We just need to write in the format of what we are given. So it can be a quadratic. Our f of x here can be a quadratic, ax squared plus bx plus c, as long the highest exponent there is what? Is a 2. For an example, f of x is equal to x squared. It's a quadratic. As long the highest power there is a 2. If we see this, we are going to present it as a quadratic as it is here. But remember that we have taken the letter a, b, so therefore, the particular integral, we're going to start from the letter c. A and b, they are being used before on the auxiliary, on those complementary function. So it's going to be c x squared, the same format, plus dx, plus the next letter, which is e. So as you can see, same quadratic format, but only that using the letters that we need. Same thing. Nothing has changed. All right, it can be an exponential. F of x can be an exponential. An exponential that is something like e to the exponent of kx. That's an exponential. For an example, y is equal to, or f of x. In this case, you can just take anything. F of x is equal to e to the exponent of 2x. It's an exponential. Whenever we see an exponential, the particular integral is going to be given as c e to the exponent of what? Of kx. That is what you're going to have there. So meaning to say we're just considering to have a c. But now, take note, there are conditions that you have if you have this, please be careful here. You are going to have something of this nature where this part of f of x that you have, remember, we're talking about this. This is f of x. So if we have anything on this f of x, take note, which is for e to the exponent of, and it is exactly the same as what we had from these auxiliary equations that we had, meaning from the particular, from this complementary part that we have. Remember, we solved these ones. And we see that the e that we are having, that we are taking here, is the same. We have something, because if you check, they're written in terms of e to the exponent of this, e to the exponent of this. So the moment that you see that the e that is here as your f of x is also appearing there as it is in terms of the power. If it is e to the exponent of 2x, they also, you have e to the exponent of 2x. In that case, you are no longer going to use this. You are no longer going to use this. You are going now to use yp of the complementary as cx. So it's going to be multiplied by x. So it's going to be cx times e to the exponent of kx. This is how you're going to expand. So like I say, this is a condition whenever you use this one. That is when part of this e is appearing, or it is part of the auxiliary equation, which is part of those complementary functions. All right? When it is part of what? Of the auxiliary equations, which is part of what? Of the complementary function. Once we see this happening, I'm going to explain if we have questions that will be like that, but be careful here. Be careful on this one. It's only for this. They will just try to confuse you there. All right. Then also it can be a condition like this, where the f of x, remember your f of x, you said it can be quadratic, it can be this, it can be that. Your f of x can also be a trigonometric function of a sine or a cos. It can be k sine x, or it can be k cos x, in any of these. In that manner, you're going to assume your complementary part as c cos x plus d sine x. So this will be your particular integral. The format, this is the format. So the constants, you must calculate the constant. All these constants that we are seeing here, they must be calculated. All these constants should be calculated. So how? So to find the constants in this case, this is it. Take note here. To find the constants on the particular solution, which is on the particular integral. To find constants on the particular integral. Remember, our particular integral is this part, e.g., for an example, we saw that the particular integral is given maybe cx plus d from the linear, whatever that you have, meaning to say you must calculate the value of c and d. So how are you going to calculate that? How are you going to calculate that? All right, so this is the idea here. You are going to relate with the original equation. This is what you have here. You are going to relate with this part of the original equation. There is dy dx squared dy dx, there is a y there. So you are going to assume that this is your complementary part, which is yp. This is dy. This is the second derivative. So as we can see that we have yp, which is this form. So we are going to need its derivative and also the second derivative. And after that, you substitute those ones in this equation, equate them to f of x, which is this one. By equating to f of x, you can be able to find the values of what? The constants. So in this case, let me just say you have, let us just write some short notes here. So e.g., y is equal to this. What you're going to do in this case, you must find first derivative of y with respect to x of the particular integral, the second derivative of y with respect to x of the particular integral. So with this y, its derivative and the second derivative, you are going to substitute. You are going to substitute these into the original equation. Into the original dE and equate to f of x. And equate to f of x. As we saw that the left-hand side of the dE is the one that has got y, dy dx, the second derivative. The right-hand side, it has got what? F of x. So you equate to f of x. Then you are supposed to find the constant or solve for constant. So in that manner, you are supposed to solve for the constants. All right, that is the idea there. By equating some variables. Let us just consider variables there. All right, we shall talk about that. We shall talk about that. Don't worry. So, as we can see that on the complementary function, we couldn't manage to calculate the constants. No. Let's go back and see. This is what we had here. We just wrote our complementary function in terms of A and B. In each of these formats, we don't know, is it going to be this, is going to be this or this? We don't know. We just wrote the complementary function. We just wrote it. In terms of A and B, that's why I wrote A and B are constants to be found. So meaning to say we do not have A and B. We still have this written as A and B. But on the integral now, on this particular integral, the constants we calculated their values, the value of C, the value of D, everything is there. So the only constants that you see are only A and B. Not C, not D, not E. Those ones, you are supposed to determine them. Whether the question needs you to find the general solution, whether the question needs you to find the particular solution, the constants of the particular integral should be given. And this is how you find them. From what? Finding of the, from that y of the particular integral, you find the first derivative, you find the second derivative, substitute into the original equation. By doing that, you can equate what corresponds to f of x, solve for constants by equating same variables. So that's the C and D is there. But A and B are not yet calculated. Take note. All right. So the complementary function at the end is going to be something that is exact. For an example, maybe you calculated C and D, you've got something like this, 2x plus 3. So it is not going to be written as constants. No, you calculated that you maybe have got 2x squared plus 3x plus 3, whatever that you have. You calculated your constants. So what are we going to do? We now combine what we calculated from the complementary function and that part of the particular integral. It gives us what we call the general solution. So we are going to talk about the general solution. That is the other thing that you're supposed to find. So the general solution is a combination of two things: our complementary function and the particular integral. But remember this, the reason that we are saying is the general solution is because our complementary function is in terms of what? Is in terms of A and B. The constants A and B are there. But on the particular integral, constants are already calculated. Constants already calculated. So it means that the equation or this part of y that we are seeing, which is our general solution, is just left with A and B as constants to be found. So we have to calculate now A and B. The calculating of A and B brings us where? To the particular solution. Remember, always we start with what? The general solution, where there are unknown values to be found. A and B, they are constants to be found. But the moment you just calculate everything, all constants are now there, or all constants are now presented. It is now the particular solution. So the question is that how are we going to have the particular solution? Because we have this as our general solution. So on that condition, remember the particular is always use the given information. Or details. Let's just say the given information. Which information are you using? Maybe you're given that y is equal to 1 when x is equal to this. The derivative of y with respect to x is equal to this when this is equal to this. You use that, but relating from the general solution. Relating from the general solution. So meaning to say, from the general solution, the purpose of everything is to find what? A and B. So you are supposed to find the constants A and B. Remember, I talked about this. So by doing this, you're done. By having the particular solution, you're done. By having the value of A and B, you are done. So are you going to memorize everything here? That's the question. Are you going to know these stages up to the last? Yes, it's possible. Very, very possible. All you need is to make sure that the first things are done properly. The determination of the complementary function up to the particular integral are done properly. You see that we have a question now, we do another question there. These questions will be familiar or will be similar somehow. There will be something that you need to relate. So these are the steps for you. All right. So we're just going to relate with these steps from the formation of the equation up to the finding of the particular solution, depending with the type of question that you are given there. But that is the idea there on the what? On the second order linear differential equation. So I think there's a question there that I'm having. This one. So we need to follow up every stage that we have discussed there. So this question was to determine or to find the general solution. So if you check here, we need the general solution of the following, which is given as 2 second derivative of y with respect to x minus dy dx. And this is minus y is equal to x squared. Okay. That's a second order linear differential equation. The format that we are seeing exactly matches the format that we are supposed to have. A dy, the second derivative of y with respect to x plus b dy dx plus cy is equal to f of x. Remember our format. And we said whenever we have this, what we need is to form or to have the auxiliary equation from this format. But how is it formed? That is the question. There are conditions that we need. And what are those conditions? All right. So you said in order for us to have our auxiliary equation, sorry, I just need this part so that we can properly see here, which is this one. All right, let's try to increase a little bit. So this is our part here. The conditions are that our f of x must be 0. Y is supposed to be 1. dy dx must be r. So in place of dy dx, we must have r. In place of y, must have 1. In place of f of x, it must be a 0. So if we let this, we are going to see that wherever there is a dy dx, that will be r. So this will be given as 2r squared. So we've got our auxiliary equation, which we formulate by letting dy dx to be equal to r, y to be equal to 1, and at that same condition, our f of x to be a 0. So that means we are going to be left with 2r squared minus dy dx, which is r in that case, minus y is 1. So this is 1 is equal to the part of f of x. This is the part of f of x, which is supposed to be a 0. So this is what we have. We have formulated our equation there, where we are supposed to solve now for r. From that auxiliary equation, you're supposed to solve it and determine the values of r. What are the r values there? So if you can see the factors, it's fine. You can have it as a quadratic, it's fine. So this is our a, b, the coefficient of r there, then c, like that. So remember that your quadratic formula, x is equal to negative b plus or minus the square root of b squared minus 4ac, everything over 2a. So x will be negative b, which is negative 1 there. So meaning to say we have got negative 1 plus or minus the square root of b squared, which is minus 1 squared, minus 4 times a, which is 2, times a c, which is minus 1. So this whole part is over 2a, which is 2 times our a, which is a 2. So this is what we have. So at the end, x is going to be what? If we simplify this, we're going to have a positive there. 1 and 1 is going to be positive 1 plus or minus the square root of. Just simplify this part under the square root. You're going to obtain a 9 and this is over 2 times 2, which is a 4. So definitely there are two solutions that you're going to have. All right, which is the first one? If we take a plus, we're going to have our x being 1. And the other value of x, if we solve, why are we having this as x? All right. You solve it as a normal equation, it's supposed to be x is equal to this, but this is now r is equal to. So like I said, we're going to have the second one with a negative, and that will be a negative half. So this is what you're going to have at the end. So this is something that you're supposed to be watchful of. Very, very watchful of. All right, no problem. So with this information that we have to compare. There are two solutions. Just going to call this R1 and this be R2. So as we saw that from this part, yes, there are supposed to be two solutions and they are supposed to be compared. Because you're supposed to have the complementary function from there. You have solved these equations, which is fine. How are the solutions given? Okay, so let's check. Are they not equal? Are they equal? Are they complex solutions that we have there? So you're going to say each and every part is going to have its own. These ones that we are having here, they are not the same. This one is 1. This one is -2. -1 over 2. R1 is not equal to R2. They are not the same. So in that case, we saw that the complementary function in this case, if they are not the same, it is going to be given in the form of e to the exponent of R1x plus b e to the exponent of R2x. And like I said, you are given this. You have this from the formula sheet. So it is something that you're not supposed to worry about, right? You're just supposed to know what you're supposed to have at the end. Like, I'm supposed to have this stage and have this stage. Then everything, you know that you have it. You are given. You have that part. So it is something that you're not supposed to even worry about. Okay, anyways, let us substitute because our R1 is there. Our R2 is also there. So therefore, we are going to have our complementary function as e to the exponent of R1, which is the solution that you have, which is 1. So this is 1x, and 1x is same as x, plus b e to the exponent of R2, which is minus half. So this is minus half x. These constants a and b are supposed to be determined. They are supposed to be calculated. But for the condition that they want us to determine the general solution, you'll see that we are not going to have to calculate this. It is something that we are just going to leave it like that. We are just going to remain with something of that nature. There's nothing that you're going to have from there. So each and every part, it is for you to consider, what am I given? How do I simplify from there? All right, so let's just put this one aside. Let's just put this one aside. What are we going to need from this or after this? The particular now. The part of the particular integral is determined from the f of x. From the f of original function. It is from the original function. So I say that you have to consider that. How is our f of x given? It determines how the the particular integral is going to be given as. So let's check. This is what we have from the original function. This whole part is equal to x squared. X squared. And that x squared is our f of x. All right, we need the particular integral. And we saw that our f of x is equal to x squared. All right, this is it. Integral. The f of x from the original function is given as x squared. So I said these are the conditions. X squared is part of the quadratic. If it was just maybe 3x plus 7, or this is a linear, 7, it's a constant, what are you given? X squared, it falls under a quadratic. So if f of x is given as a quadratic, whether it's x squared only, whether it's given as x squared plus 2x plus 3, that does not matter. As long the highest power there is a 2, you are going to take your complementary function as a quadratic, which is cx squared plus dx plus e. I explained about starting from the letter c. It is because we have used letter A and letter B. So the only part to start, it will be letter C, because we've used A and B. So it's a quadratic. It's of the format ax squared plus bx plus c. This is the format. So therefore, the particular integral in this case is going to be given as a quadratic also, which will be cx squared plus dx plus e. And I said that on this one, you are supposed to determine the solutions. You're supposed to determine the value of the constants. Is different from this of the particular, of the complementary function, this one. Here you don't do anything. Complementary function. You don't do anything here. You see it later on. Here you must find C, find D, find E. From where? Since this is our YP, we are going to substitute these onto this part of the original function. Remember our original function, the way that it was given. The way that it was given as it is. So we're going to take that part. Our original function was given as, so you go back to the original function. Relate to the original function here. So you relate to the original function. How? That's the question. The original function is given as 2 the second derivative of y with respect to x minus the derivative of y with respect to x minus y is equal to x squared. So what we need is to substitute. So we are going to let this to be yp, representing the particular integral. So this will be the derivative of y with respect to x of the particular integral, the second derivative of y with respect to x of the particular integral. Then we substitute in that original equation. So as you can see, yp is already there, which is this one. So what we need is its derivative. So you're going to find the derivative of y with respect to x of the particular integral. I talked about this, everything here. With this yp that we have, we said in order for us to find c and d and e, whatever that you're given there, for an example, you've got something like this and you need to find the constants. You need to take that yp, find its derivative, second derivative, substitute this into the original dE, which is the original differential equation, and equate to f of x. Solve for the constants by equating Same variables. This is it. Same like terms. So we need to find the derivative of y with respect to x with this. So what is the derivative of y with respect to x? Drop the exponent, so this will be 2cx plus this will be a d here. E, it's a constant, the derivative of a constant, that's a 0 there. What we need is the second derivative so that we can substitute there. So we are going to need the second derivative. 2cx. So it's going to be 2c, d is a constant, so that's a 0 there. So we have y, its derivative, its second derivative. So relating or substituting back into the original equation, it means this will be 2 into the derivative, the second derivative of y with respect to x, which is this one, of the particular integral. Second derivative there is what? It's 2c minus dy dx, the derivative of y with respect to x of the particular integral, which in this case we got 2cx plus a d, minus yp, which is y in this case, y representing or represented by yp is that of the quadratic that we took, which is cx squared plus dx plus e. So we substituted into the original differential equation. So this must be equated to exactly what is on the right-hand side, which is our f of x. So it's an equation that we can use to determine the values of of C, D, and E. How? Let's expand and see. So if you expand this, that will be 4C here, minus 2. If you subtract this, it's going to be 2cx negative times d. It will be negative d. Negative times this and this, it will be negative cx squared. Negative times this, it will be negative dx. Negative e like this is equal to x squared. So this is what we have now. So by just looking into this quadratic that we have, which is we are supposed to have ax squared plus bx plus c plus and so on. So we do not have the part of x, it's going to be 0x. The constant just going to be a 0. So let's start with the coefficients of x squared. Considering x squared on the left-hand side on these constants, what is affecting x squared? The coefficient of x squared, the variable that we have is x squared, but what is the coefficient affecting x squared? That's minus c. It must be equal. Do we have anything in the left-hand side of x squared? No, it's just this one. And what we have on the right-hand side, the coefficient of x squared, there is a 1. So minus c must be equal to 1. So if we divide by minus 1, it means c is what? C is minus 1. All right. With the same concept, let us move on to x. So you're going to talk of the coefficients of x in this case. So the coefficients of x is what is affecting x. This is it, the coefficient, which is what? Minus 2c, coefficient of x here. The coefficient of x also on the left-hand side, we have to check everything on the left-hand side. There is another one, which is what? Minus d. This is the coefficient, the number, the term affecting x is equal to what is affecting x on the right-hand side. We do not have x there, so it means we've got what? A 0. So that's we've got a 0 there. So having the value of c that we calculated and got a negative 1 in this case, we can be able to calculate the value of d, because this will be negative 2 times 1, which is a positive 2, minus d is equal to 0. So d will be equal to 2. All right, so we have C, we have D, we are left with E, stage by stage. So we started with the coefficient of equating part of x squared. We moved on to x. So this time we're going to relate with the constants. So on the left-hand side, the constants, that is, we do not have x, we do not have x squared, is just a letter that we have. So we take all the constants on the left-hand side. There we've got 4c another constant minus D, another constant minus E. These are the constants that we have. It must be equal to the constants also on the right-hand side, and the constant there we do not have, so it's just what? A 0. If the part is not given, you equate that to a 0. Having the value of C, which is -1, having the value of D, which is a 2, we can calculate the value of what? Of E. So that's it. So this will be -4 minus 2 minus E is equal to 0. That's -6 minus E is equal to 0. So E is going to be a +6 there. All right. E is going to be a -6, I mean, because it's going to be this side. So it will be a -6. So that's it. You have got your E there. From C to D to A. So the particular integral, it must have the values of the constants, C, D, and A, whatever that you have. It is only the complementary part that you have to leave it in terms of those constants A, B, A and B. So therefore, let us rewrite this, because remember, we said this particular integral was given as, remember the format that we had written here, it was given as what? Yp is equal to this, cx squared plus dx plus E. So therefore, from that part, we're going to have this as, so therefore, we're going to have this Yp as, so therefore, our Yp is going to be, remember, it was given as a quadratic cx squared plus dx plus E. And we calculated everything. So our C, that's a -1. So it's going to be -x squared. D, +2. So this is 2xe, which is -6. All right. So that's it. So this is always like that in each and every question that you are going to attempt. All right. Sorry for that, guys. So this is, guys, this software things, but that is what you're going to have. So the particular integral, this one that we are given here, is always like that. Like I explained, that it is supposed to be C calculated, D calculated. If there is E, also E is supposed to be calculated. These constants should be there. They must be there. All right. So now that we have got these particulars now there, the complementary function is now there. What are we going to have at the end? The general solution. Remember from our notes, we said the combination of these two gives us what? The general solution, which is y is equal to yc plus yp. So that is the last part that we need, since the question was on the general solution. So therefore, our general solution, which is y is equal to yc plus yp. Complementary function plus the particular integral. So y is equal to, remember this one, it must contain a and b because we never calculated those ones. So we're going to take it from here as it was here, ae to the exponent of x plus be to the exponent of half x. That is what we had from that equation. If you still remember, ae to the exponent of x plus b to the exponent of minus half x. Plus now the particular solution where we solved these constants. So this one is going to be like this. So having this equation with the constants a and b to be calculated, that's the general solution. The moment you calculate a and b, these ones, you are now having the particular solution. So that is where we were supposed to have our solution up to. Just like that. Just like that. So as we can see, it is something that is, you have to be careful. You have to be careful. What is it that you're supposed to determine? How do you determine that part? That's the case. So there are so many questions, so many presentations. Like I said, it'll need us to have as much time as we can so that we'll be able to properly talk about this. We need as much time. The other question was to determine the particular solution given this. Again, second order that we have there. So you say the first thing in this case is to find the auxiliary equation by letting the part of dy dx to be equal to what? To be r, y to be 1, and our f of x to be equal to 0. All right, so as you can see, our f of x there is a constant. This is your f of x there, which is a constant. So this will be r squared minus 2 dy dx, which is r there. Y is represented by 1, as I said, and that is a 0 there in place of f of x. Even if it's a constant, you write it as f of x, which is 0. So that's our auxiliary equation where we are supposed to solve this and determine the values of r. So using the quadratic formula or even factorization, if you check your factorization can just be direct. The coefficient of here's 1, so it's going to be r times r, which is r squared. The factors of positive 1, and these factors should give us what? A negative 2, that is negative 1 and negative 1. If you multiply this, you get a positive 1. If you add, you get a negative 2. So one of these brackets must be a 0, so it means r must be 1 or r must be also a 1. These solutions are equal, they are the same. So we've got same roots, same solutions. So if the roots are the same, or if the solutions are the same, what is the case? Let's go back to the complementary. Because we know that the complementary function has to be related from the auxiliary equation. And what is it that we have from the auxiliary equation? From our auxiliary equation, here, I'm going to have a lot of things. Very sorry for that. I just want you guys to understand this. We say these are the conditions about the auxiliary, where you have to now figure out your complementary solution. Okay, guys, I now dragged this too much. As you see, there are a lot of things now here. All right. Let's just hope you be able to understand me. All right, this is the one. So here we are going to see that we saw that the two solutions are the same. R1 is equal to R2. So this is going to be our presentation of what? The complementary function. Because R1 is equal to R2. The solutions there are the same. So what does it mean? Okay, so let us just have it here. So since R1 is equal to R2, we were supposed to have our complementary function as e to the exponent of Rx into a plus bx, where this r is the same one, because it's the same that we have here. So it means yc is going to be e to the exponent of 1x, so it's just x there, into a plus bx. We have this from the formula sheet, like I said. There is nothing that you calculate here, only expressed like this, you are done. Just leave it like that. That's your complementary function. From our f of x, we need now to determine the particular integral from this side. So to have our particular integral, we need, in this case, f of x. F of x. Where is our f of x? Our f of x is a constant, which is 8. So given that our f of x is a constant, which is 8, what about yp? So it's just going to be equal to c. Remember what we said here. If your f of x, which is the original function, is equal to k, therefore the particular integral is c, just a constant. But you must find that whatever that you have, you must find that c. You must find that c. From where now? That is where I talked about the issue of the first derivative, because this yp that we are seeing, it is the same as this y. So we need its first derivative, its second derivative. So what will be the first derivative of y with respect to x of the particular integral? It's a constant. There's no x here. It's a constant. So that's a 0 there. It's nothing that you're getting. There's nothing that we are obtaining from there. Okay, guys, let's just hope this is going to win. We're just going to win. So you see these softwares, guys, they are problem. But let's just hope we're going to win. Just almost done. So this is it. That's a constant. So the derivative there is that's a 0. Second derivative, again, with respect to x of the particular integral, if you differentiate a 0, there's nothing. It's just going to be a 0. So like I said, you need to substitute this back into the original equation that you are given there. That means in place of the original equation, this is the second derivative. But is there anything? No, the second derivative is a 0. So that's 0 minus 2 times the first derivative of y with respect to x, the first derivative of y with respect to x, that's a 0. Plus y in this case, where y represents c, which is the part of the particular integral. Yp is equal to c. So this must be equated to f of x, and your f of x there is what? It's 8. So that's it. So as you can see in this case, that's a 0 is 0. So c is equal to what? C is equal to 8. So this one is just direct. The 8 that we had, that is our c. So therefore, yp, which is our particular integral, is going to be equal to 8, which is equal to c, the one that we calculated here. All right. With the complementary function, the particular integral, these two together, they are combined, joined to give us what we refer to as what? As the general solution. So here we said after this, you're going to need the general solution. And the general solution, it is a combination of these two, complementary function and the particular integral. So that is y is equal to e to the exponent of x into a plus bx, like this, plus yp, which is our particular integral. We got what? That one was direct. It was just 8. But this is not our question. The question is not focusing on the general solution. No. The question is based on determining the particular solution, provided that x is equal to 0 when y is equal to 1. That's the first thing there. X must be a 0 provided that y is equal to 1. It's a condition. Another condition, which is a separate condition, is that the first derivative of y with respect to x must be 1 when x is 0. So the derivative there, you are given a condition to use from the general solution. The derivative of y with respect to x must be a 1, provided that x is a 0 there. Did they say 1 or a 0? Sorry for that. 1 when x is 0. So the first derivative is 1 when x is what? When x is a 0. So it's another condition. So let's use the first condition. So where do we use it? In the general solution. We have it in the general solution. So now I'm going to find the particular solution. That's it. It's now a solution. This one is not an integral. So take note. So let's start with the first condition. X is a 0, y it's 1. Y it's 1. When x is a 0, so that's e to the exponent of 0 into a plus, that's a 0 there, plus 8. E to the exponent of 0, that's a 1. So if I transpose this, a to this side is going to be 1 minus 8, which is minus 7, is equal to, here we'll be left with a plus 0, which is a, times 1, which is just a. So I have got the value of a. So to find b, I'm going to this condition. This time they need you to find dy dx where x is 0. Where from this y that we are given of the general solution, we are supposed to determine the derivative there of y with respect to x. So as you can see, this is a product that we are having on the first two. So the derivative of y with respect to x, gonna use the product, gonna start with you can even start with v, whatever that you want. You can start with u, e to the exponent of x times the first derivative of v, which is this one. It's a constant, so that's a 0. The derivative of bx, it is going to be b, plus we take our v as it is, the function of v, which is a, plus bx, times the first derivative of u. Remember, the derivative of e remains like that. Then 8 is a constant. This one is, we are done with the product of this. Then we move on to the 8. It's just a number, that one. So the derivative of 8 is what? It's a 0. So there's nothing there. There's nothing here. So this is our derivative from the general solution. So from this, the derivative of y with respect is 1, of y with respect to x is 1, where x is a 0. So there we're going to put a 0, e to the exponent of 0, that's 1. 1 times b, that's a b. Here we're going to have a 0 there. There a 0 there. E to the exponent of 1, it's 1. So it's 1 times a, which is a. The b is gone because of x, which is a 0 there. So 1 is equal to a plus b, but we calculated a before and we got a minus 7. So transpose to the other side is going to be a positive 7. So that's 1 plus 7, which is 8, is equal to b. So that's if b is 8 and a is given as minus 7. Therefore, we can write now our particular solution now as therefore y is equal to e to the exponent of x into a, we calculated our a, we got what? Negative 7, plus bx, our b, which is 8. So this is 8x, plus what? 8. The constant 8 there is from our particular integral. Remember that particular integral. So this one cannot be simplified. You just have to leave it like that. So this is how we determine the particular solution. So like I said, it is the general solution first. From the general solution, you use the given information the way that is given. How are you given it? So finding A and B means we have what? The particular solution. So we shall see more questions about this. I think now we have got a basic part to even answer as much questions, even some of the other questions that we have done before, but because you're not having an introduction, you can now understand them. But we shall have as much questions as we can from there.